So now we continue. So last time we started to calculate the real space spatial correlation functions of Ising spin in one dimension, and we derived this spatial correlation functions for these two spins at any two given sites, and as a function of this dimensionless couplings K. And in particular, we find that the nearest neighbor spatial correlations as function of K behaves as this hyperbolic tangent function. In the zero temperature limit, it approaches 1. In the high temperature limit, it decreases to 0. And we also show that the only place where you have a phase transition is at zero temperature and zero field limit. In particular, we show that the correlation function for the two sides I and say I plus j versus k, which is hyperbolic tangent function, but this is hyperbolic tangent k to the power of j, where j is the distance between these two sides at I and I plus j. So you can see very clearly that the correlation gives the 100% probability of finding these two spins having the same value in the zero temperature limit. And we also can define this correlation length, and it diverges exponentially as temperature is reduced to 0. So today we will use another method called transfer matrix method that we introduced earlier to calculate this Gij once again. Okay, so you will see that you could have the same conclusion but different approach, and you appreciate how useful and convenient this transfer matrix can take us. Right, so remember when we calculate this expectation value of a single spin on site I for a one-dimensional Ising model, this is by definition is given by this ensemble average, and you could see that this Si is somewhere here. And you could use this transfer matrix to represent all this product of all this inside this summation, and you get this kind of a transfer matrix product running from S1, S2, S2, S3, TSI, TSM minus 1 as n. But then the most important term is the term that is related to the Si, which is circled here. Si is sandwiched in between this TSI Si minus 1 and TSI Si plus 1. So if you look at this matrix structure of this product concerning this Si site, you'll see that this is simply a matrix element of a matrix product, which I call this A, matrix A, which is made of matrix product of the three matrices. Two of them on two sides of this expression is simply just a T or transfer matrix, but in the middle we have a Pauli spin matrix, which has the plus 1 minus 1 along the diagonal and 0 along the off diagonal. If you simply just expand all these matrix elements of this three matrix product, and you get back to this form. Okay, so we're going to take advantage of such a matrix product when we evaluate this single spin expectation value. And once we have done that, we will generalize it to the spin correlation functions, where we have two spin on different sides, and we take the expectation value of that spin-spin correlator. So come back to the single spin expectation value. So if you look at the matrix structure of this ensemble average, and you'll see that this is nothing but the trace of the sigma z multiply t to the power of n, because all the transfer matrices are identical as we mentioned previously, that all these T matrices have the same matrix elements. So you simply just multiply this transfer matrix to the power of n and multiply sigma z. And when you take the trace, it doesn't matter ordering of this matrix products. For example, if I take the trace of these three matrices A times B times C, it is the same as matrices C times A times B, and so on. So in other words, you could just permute this ordering of these three matrices in a cyclic order, so that the trace of ABC is the same as trace of CAB and same as trace of BCA, and so on and so forth. As a result, you can simply just rearrange all this T matrix or chance matrices inside the trace such that the sigma z appears in the front, and then to multiply sigma z by t to the power of n. As we mentioned previously, that the reason why we introduce the chance matrix is that we can diagonalize this T matrix or chance matrix by a unitary transformation, which we call this S matrix. This is a unitary matrix which will diagonalize the chance matrix T by a unitary transformation. Here, when we apply this unitary transformation on this T matrix, and the T matrix becomes T prime, but the T prime matrix is actually diagonal. And that's how we find these eigenvalues, lambda 1, lambda 2. And we can also find the eigenvectors associated with these two eigenvalues. And if I use this x1 represents the eigenvectors for lambda 1, which is a column 1 by 2, 2 by 1 column matrix with the matrix elements A and B, and x2 is the second eigenvectors for the second eigenvalue, lambda 2, which has this matrix element C and D. And we simply just combine these two eigenvectors in this fashion, and we could make a unitary matrix. And then we could show that this T matrix becomes T prime, which is diagonal. So now we could use that trick to actually rewrite this trace when this T is actually diagonalized. Okay? Namely, we could just use this unitary transformation as inverse S acting on this trace inside of the trace, and it will transform all the matrices inside the trace. But this T will become T prime, but we have n's power of T, and therefore this is T prime to the power of n. But we also need to transform this sigma z by this S matrix. And suppose that we don't know the answer, and we simply just use some symbols E, F, G, and K to represent the resulting transformed sigma z matrix. And we simply just plug in this E, F, G, K 2 by 2 matrix back to this expression value of a single spin, and taking advantage of this diagonal matrix T prime, and then you get to this result. Okay, so this is actually kind of a shortcut to the calculation, taking advantage of this transform matrix and this diagonal basis. And so you can see that we know very well that lambda 1 is actually greater than lambda 2. So in the thermodynamic limit, when n goes to infinity, you see that all these lambda 2 factors go away because it is nothing compared to lambda 1. As a result, the single spin expectation value in the thermodynamic limit for Ising chain is approximately given by this matrix element E, which is a function of temperature, field, and coupling constant. Good. And we could simply take advantage of such a single spin expectation value, and we keep calculating the two spin correlation function, where this two spin could be anywhere. So this is a two spin correlator which measures the probability of having these two spins on side I and I plus j having the same value. Okay, but you could use this definition that we calculate for the single spin expectation value, which is simply just 1 over z times this trace of this matrices. Okay, so this is S inverse sigma z S T prime to the power of j, and S inverse sigma z S T prime to the power of n minus j. Okay, so I don't spend much time in deriving this, but you could simply just use a similar way of deriving the single spin expectation value. You could verify easily that this is the resulting matrix inside the trace of a two spin correlation function. And you know what this is for each of these brackets. S inverse sigma z S is nothing but what? This EFGK, right? So this is EFGK. And this is also the same 2 by 2 matrix. And what is T prime? T prime is that lambda 1, lambda 2 diagonal 2 by 2 matrix, and you simply just combine everything and multiply this 1, 2, 3, 4 2 by 2 matrices. And you take the thermodynamic limit and goes to infinity, and Si plus j is approximately given by E squared plus G times F lambda 2 divided by lambda 1 to the power of j. Okay, so let's take a short break. When we come back, we will continue finishing this calculation of two spin correlation functions, where the two spins can be anywhere on the chain by using the transfer matrix method. Okay, let's take a short break. So from the previous derivation, we know that for a single spin, the SI expectation value is approximately given by this E, this matrix element for this S matrix, E, F, G, and K. But for the two spin correlator, Si plus J, in the thermodynamic limit is given by E squared plus G times F times lambda 2 divided by lambda 1 to the power of J, which follows in a similar way that we derive the single spin expression value. But we need to calculate Green's function or correlation function, Gii plus J, which is defined by this expression that we defined already, which is the spin-spin correlation function subtracted from the product of the single spin expectation value, Si average times Sj average. But Si average is E, so is Sj average. All right? And as a result, if you simply just subtract one from another, you get cancellation of the E squared term. And then as a result, you only have this Gf times this lambda 2 divided by lambda 1 term remains, which can be re-expressed in terms of exponential function, e to the minus j times log of lambda 1 divided by lambda 2. Since lambda 1 is actually larger than lambda 2, so you can see that this Green's function, the correlation function, for any given finite temperature as a function of distance j decays exponentially. Okay, so this is e to the minus j, which is the distance between these two sides, I and I plus j, and this decay is actually exponential form. Okay, e to the minus some constant times j. Okay, so this agrees with our earlier results that there's no long-range order at any given finite temperature for one-dimensional Ising chain, because the correlation which measures the probability that you have these two spins at any two given sites having the same values, and that probability actually decays exponentially and decreases to 0. So there is no probability, the probability is 0 to find the two spins at any given distance to be at the same value. Okay, and therefore these two spins do not correlate, are not correlated. Okay, there's no correlation between these two spins for any given finite temperature. So we can keep checking this correlation function by setting the field to be 0 in the zero field limit, and you see that the lambda 1 is actually 2 coach k and lambda 2 is actually 2 sinh of k. As a result, the correlation length c, which is defined by 1 over log of this ratio between lambda 1 and lambda 2, which becomes 1 over log hyperbolic cotangent of k, which is exactly what we found last time. All right, okay, so you can see that the correlation length diverges as temperature is decreased to 0, and then we have a long-range order, and at the same time, the transition temperature, Tc, is actually at exactly 0 temperature. Okay, so that's the end of our story for one-dimensional Ising chain. And we learned the lesson that if we follow the statistical mechanics textbook, we calculate this partition function for one-dimensional Ising chain, and we could use the transfer matrix method, and we can define this correlation function, and we find that the phase transition is at 0 temperature, 0 field. Okay, let's just generalize this Ising model to higher dimensions, and it could be at d-dimensional Ising model, and see what it happens. So we'll see later that this transition temperature for, say, a two-dimensional Ising model is at a finite temperature. But let us just provide an example that we could exactly solve the system. Okay, so say exactly solvable Ising model. And you'll see a very beautiful results come out of this exactly solvable limit of the Ising model. And after that, we could use some approximation, say mean field theory, and for a more realistic, say, Ising system. So this Ising system, which supports this exact solution, is actually a very special Ising model, where the Ising coupling is actually infinitely long range Ising coupling. So you will see that in the thermodynamic limit, this infinitely long range Ising spin system can be solved exactly. So this is infinite range Ising model. So the first term is the Zeeman term. That's not special, but the special point is the second term, which describes this Ising coupling. And you can see that the Ising coupling, Si, Sj, which are independently summed over all the sites, I and j. So this tells us that this interaction is actually infinitely long range, which means that for any given site I, there's a nearest neighbor interactions, and there's a second neighbor interaction, and third neighbor interaction, and fourth neighbor interaction. Because if you fix the site I, then j runs from 1 to n, which means that the j could be any sites, all the sites along the chain, or on the square lattice, or on the cubic lattice, whatever the lattice is. And j is actually independent of I. It doesn't imply the j, we don't restrict the j to be the nearest neighbor site, but j could extend to all the lattice points. So in other words, it is actually an infinite long-ranged interaction. So imagine that we could allow the spin to interact that long range with the same coupling constant. So this is really a toy model. So we know that in the realistic system, the longer the range, the weaker the interaction will be. So that's our explanation for the long-range spin coupling. But here, we artificially consider a toy model such that all these couplings for all distances is actually identical. So J0 is J divided by M. Okay? And we sum over all possible I and J, where I and J could be the same site or different sites. So of course, this is related to the Ising system that we just studied, but it is not exactly the same. So it is something else that we consider infinitely long-range Ising coupling. But the nice thing about this toy model is that in the large n limit, where n is actually number of sites, this Hamiltonian supports some exact solutions. And we'll see that in just a moment. So we could try to calculate this partition function of such a toy model by this kind of a trace of the Boltzmann weight. And if you look at the matrix inside the trace of the partition function, you notice that the summation over I and j are actually carried out independently, and therefore you can simply just square of the sum over I for the second term. All right? Okay, so that actually leads to some exactly solvable limit of this model. Again, we define this dimensionless couplings H, which is a reduced magnetic field, and K, which is dimensionless Ising coupling. So the following job is actually to carry out this summation of Si for this exponential term. But we could take advantage of a Gaussian integral, which is this identity here. So exponential function of this x squared in the exponent multiplied by a prefactor is given by this Gaussian integral. This integral is for the parameter y. When you evaluate this Gauss integral over y, and you get back to this e to the a divided by 2n times x squared. So this is called Gaussian integral. And I'm sure that all of you have seen this kind of a Gaussian integral when you study mathematics or applied math. So here, the constant a, in our case, is actually the reduced Ising coupling k, and x is actually sum over I si. So if you simply just plug in this definition of a and x back to this integral, and you could actually rewrite this partition function in terms of the integral over y. So you could check this by completing the square. Namely, if you complete the square, you could see that this is simply a square, the full square of the y minus x over n times the prefactor with a minus sign and plus the x squared term, okay? And the full square appearing in the exponent of the exponential function of y when you integrate out the y degrees of freedom, and you get just a constant, okay? Square root of the pi divided by some constant, which is related to the na divided by 2, all right? So which is precisely this prefactor here. All right, so let's take a short break. When we come back, we'll continue taking advantage of this Gaussian integral and rewrite this partition function for an infinity range Ising model, and then we'll see that this actually supports the exact solution when n goes to infinity. And we will derive this critical exponent of such a toy model in just a moment. So before the break, we'll derive the partition function of an infinity long range Ising model, arbitrary dimension, and we would like to take advantage of this Gaussian integral by replacing the e to the minus x squared, that term in the partition function, by the integral over y, and where y is actually a continuous variable ranging from minus plus infinity. And then we try to analyze this partition function in terms of the integral over y. And if we plug in this Gaussian identity involving this Gaussian integral by completing the square in the exponents of the exponential function inside the partition function, then we could rewrite this partition function in terms of this y variables. And this is the result. Okay, so then the next step is to sum over the spins every site I, where si plus or minus 1. So you could simply just combine the last term in the exponents of the exponential function of a y and the first term, which we don't change. All right, so these two terms are effectively the Zeeman term, which we'll call this alpha. If you sum over this e to the alpha times sum over isi, and you sum over the si, you get n's power over 2 times hyperbolic cosine of alpha that we already derived a few lectures ago. All right, so then you can rewrite this coach function in the form of the exponential of this log to coach of alpha and with a prefactor n. You simply just plug in this resulting expression after summing over the spin si and back to this partition function, and you get that form. So now the partition function is written in terms of the integral over a continuous variable y, and we need to integrate over this continuous variable y ranging from minus to plus infinity. And the remaining job is to find a way to really evaluate this integral, right? So this is a highly non-trivial function of y, exponential function of y, and also the exponential of the log of a coach function of the field and coupling constant times y. So this is a bit complicated function of y, but fortunately, in the limit of n goes to infinity, which corresponds to the thermodynamic limit, this partition function could be done exactly by a method called the steepest descent method or the saddle point method. So in other words, this function e to the something function of y, f of y, may have some saddle point like this. But of course, you could check the plots of this f function or e to the f of y by a computer or Mathematica. But this is just an example that you may have a functional form like this, or minima, or maybe a maxima, something like this. So a saddle point is the point where the functional form has the zeros of the first derivative. So if I call this g as function of y, partial gy partial y, it's actually 0. So it could be a minima, a maxima, or a saddle point in terms of a multidimensional function where if you imagine that we have a function f, which is a function of x and y, and in certain direction it is the maximum, but along another direction it is the minimum. So a saddle point is defined by a following way, that it is a maxima point along one direction, say alpha, but it is the minima point along another direction called beta, where alpha and beta is actually a vector in this multidimensional manifold. All right? Okay, so you could check whether this exponential function of y has indeed a saddle point. If there's a saddle point, then we could simply just take advantage of saddle point property, that the first order derivative of that function with respect to the parameter, which is y here, vanishes. And then we could simply just use that as an approximation to actually evaluate that integral over dy. So it is called a steep descent method, or saddle point approximation. So we should find such a saddle point where the partition function could be approximately given by this. So this approximation becomes exact in the large n limit. Okay, so that's what we call this exactly solvable limit, where this large n, partition function, a saddle point, a solution where the saddle point gives rise to a minimum of free energy. So existence of this saddle point, which we call this y bar, in this case, we hope and we expect this will be a minimum point of free energy. And this is the variable y, which minimizes the free energy, which is defined as this way. Okay, so if there exists such a saddle point or a minimum free energy point, and at that point the free energy, which is minus kb t times log of this partition function, is actually minimized. Okay, so in that case we could take advantage of this minimum point of this free energy functional as function of parameter y, and then we take the first derivative of this free energy with respect to the parameter y, and it will become 0 at that minimum point or saddle point. So therefore you get df dy at y bar is actually 0, and this is actually minimum of a free energy. We could use that condition, so-called saddle point equation, and we try to minimize the free energy with respect to this y and get a minimum point and get a solution y bar which satisfies this saddle point equation or condition. So when we take the first derivative of f with respect to y, you get this. You set this advantage of this first order derivatives f with respect to y, and then you rewrite this condition in terms of this equation here. This is called the saddle point equation, and try to solve the saddle point equation and look for the solution that satisfies the saddle point equation. And if we could really find such a saddle point, a y bar, which satisfies this equation, then we're done. And then this is our solution of the Ising model of infinitely long range interaction. So let's take a short break. When we come back, we will continue trying to solve the saddle point equation, toy model. Let's take a short break. So before the break, we derived this partition function by rewriting the partition function in terms of the Gaussian integral over dy, and we said that in the thermodynamic limit where n goes to infinity, this integral could be shown that it is given by the saddle point value. Okay, so let me just explain how to actually get to this conclusion. So if you define saddle point y bar, which can minimize the free energy, and we know that in statistical mechanics, free energy at minimum point usually is negative value. Okay, so in order to minimize the free energy, to actually maximize the magnitude of the free energy. In other words, if you consider this free energy taking at a minimum point, because there's a minus sign here in front of the other factors, including this free energy. So minimum value of free energy is actually negative, so double negative is actually positive. So which means that the integral over dy partition function at a set of point or a minimum free energy point, it is actually a positive value in the exponents of the exponential function. So, and then we say that we could forget about the other values and other y away from this set of point or minimum point of a free energy. So the integral is completely determined by the set of point value of the free energy. Okay, because in the n goes to infinity limit, this exponent is actually divergent, right? So which means that you don't need to care about all the other values apart from the, say, set of point, y bar. So suppose this is a landscape of the free energy as function of y, and suppose we found the minimum point which minimizes the free energy is located at y bar, and the set of point approximation tells us that you could certainly just consider the partition function, evaluate it right at that set of point, y bar, and you could neglect all the contributions from different values of y away from y bar. So in other words, the contributions to the partition function in the integral over dy, different values of y away from y bar is actually negligible. So we could altogether simply just forget about all the contributions coming from different y values from this y bar in the partition function. So, and this is certainly an approximation, but this approximation becomes exact in the Lagrangian limit when n goes to infinity. As I mentioned, when n goes to infinity, we certainly don't care about the other contributions, because at this minimum point, free energy is actually minimized, and which oftentimes acquire a negative value, and in other words, the exponent in the exponential function of a partition function is actually a positive value, and as a result, it gives the leading order contributions to the integral over dy. And that is the reason why we call this model exactly solvable in the Lagrangian limit. And we simply just forget about the other contributions from other y values, and by looking at just the partition function at that set of point y bar. Okay, and we define such a point by taking the first derivative of free energy with respect to y and take it to be 0. And in that case, we get this condition, which we call the saddle point equation, and we try to find whether we have a solution or not by analytical or numerical method. Suppose we find such a solution which satisfies the saddle point equation, and we could take advantage of such a solution, and we could obtain the magnetization or spin moment after ensemble average. So the single spin expression value over entire lattice is given by this derivative of this log z divided by respect to this h, where h is dimensionless field, divided by beta times n. So if I simply just use a saddle point expression for this partition function, then this is simply given by this hyperbolic tangent function times this beta n, but you need to divide this by another beta n. So, and therefore you get this hyperbolic tangent function, but you know that this hyperbolic tangent function, if you really want to solve this y bar, this has to be y bar. So this is y bar. And therefore, if we find the y bar, and this y bar is simply just a single spin ensemble averaged value. All right? So that's really magic. So let's try to solve this saddle point equation. To solve this, a smarter way is to actually use a plot or figure to actually find an intersection between two curves. One is a linear function in y. Another is the hyperbolic tangent function. suppose this is the line which shows that this is y bar. So the yellow line represents the function which is y bar, and the hyperbolic tangent function is indicated by dashed line here. So this is the hyperbolic tangent function, one possible solution, and another is something like this. So you want the intersection between these two curves. Y is actually equals to y bar. Another is that y is actually hyperbolic tangent function. And you try to find the intersection between these two curves, and if you find this intersection and you find the solution, and if there's no intersection, then there's no solution. So that's really simple. And you see that there are actually, in general, 3 intersection points that could be found. So in the case of the red curves, where you can see that the yellow line intersects with the red curves by the 3 points, 2 squares and 1 circle, and this is the case in the high temperature regime, right? So in the high temperature regime, when beta j is actually larger than 1, sorry, this is the low temperature region. Orange curve is actually the high temperature region where beta j is actually less than 1. So this is the high T region. So in the low temperature regime, the curves follow the red curve, which intersects with the yellow straight line by 3 intersection points. One that's 0, which is the trivial solution, which says that y is actually 0. There are 2 non-trivial solutions, which gives rise to the finite maximization. Okay, so there are 3 solutions. One is trivial, another is actually non-trivial. Y bar is actually hyperbolic tangent function, which is plus minus some value here, which indicates that the system breaks the rotational invariance spontaneously. Okay, so you get the long range order in the low temperature phase, but in the high temperature, there's no long range order because y bar vanishes, and you know that when y bar vanishes, you get no expression value of a single spin after you take the ensemble average. And therefore, you get the phase transition. So the phase transition occurs exactly when the beta j is actually 1, okay? Which in terms of the Tc, or transition temperature, this is J divided by Kb Tc. So in other words, when J is the same as Kb Tc, you get a phase transition. So when T is larger than Tc, or this value, and you actually end up disordered phase, but when temperature is lower than Tc, you get the ordered phase. So Tc is what? J divided by Kb. Okay, so we finally get the solution out of the infinity long range Ising model in any dimensions, and we find that in general we can have a phase transition at finite temperature, and the critical temperature is found to be J divided by Kb. Okay, so next time we will continue calculating other observables such as critical exponents and so on, and thermodynamics, and we will understand critical phenomena of such exactly solvable Ising model. And then after that, we will come back to reality. We consider any dimensional Ising model, but instead of exactly solvable limits, we actually solve the model by using the mean field theory. Okay, and where mean field theory makes some approximations, something like saddle point approximation, but then we don't have the exact solution anymore, but we need to neglect some fluctuations above the mean field solutions, and we only keep these mean field solutions, and then we will analyze again the critical exponents of a mean field Ising model, And then we can compare the critical exponents of a mean field theory with the model that we just calculated for the exactly solvable infinitely long-range Ising model. Okay, and then after that, we will start to introduce the Landau theory, and then started the field theory approach to the phase transition formally. So I'll see you next time.